2.4 is the last section in chapter 2. So let's go ahead and do this. So we are doing correlations, scatterplots, and regression. So you'll recognize all of these words from college algebra and algebra 1, algebra 2. But we are going to look at it from a statistics stance, but still looking at the same definitions and terms. So a scatterplot is a plot paired x, y, quantitative data with a horizontal x-axis and vertical y-axis. Horizontal axis is used for the first variable x. Vertical is for the second variable y. Correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. So there is a caution here. The important caution is correlation does not imply causality. So correlation and association doesn't mean that just because they're associated, one causes the other. So there's not necessarily a cause and effect relationship there. It says we might find a correlation between beer consumption and weight, but we cannot conclude from the statistical evidence that drinking beer has a direct effect on weight. So just because you drink beer doesn't mean you're going to gain weight. So as you notice, with these concepts and statistics, sometimes you're going to see some more adult-related concepts. So that would be one of them where it's talking about beer, which you wouldn't normally see that in a high school class. So let's look at our example, waist and arm correlation. So we have our x variable is waist circumference, and then our y is arm circumference. So this correlation, it looks like a positive correlation. Positive linear correlation. So it looks like we could kind of draw a line. So basically what this is saying is the larger your waist circumference or the longer the circumference is, the longer your arm circumference. So that's kind of like the bigger around you are, the bigger around your arms are as well. Weight and pulse rate. So this one is all over the place. There's no straight line in there. So this would have no correlation. There's no correlation between weight and pulse rate. Okay, the correlation coefficient. This is where we can use the R as our letter that represents it. So we have the R values are between -1 and +1, and it shows how closely the points on the scatter plot fit the pattern of a straight line. So if it's close to a +1, then we have a strong positive correlation. Close to a -1, strong negative correlation. And if it's close to 0, there's no relationship between the variables. And this gives you an idea of what it's going to look like. So positive correlation of 1 would be a straight line. -1 would be straight line as well, but it's going downhill. 0 is that no correlation. And then it kind of gets spread out the closer you get to 0. The closer you get to 1 and -1, it follows more closely to a line. And we know how to do this with the calculator. We're going to go over those steps. So we are going to use this information right here. So this is shoe print length and height. So grab your calculator. And we are going to plug the data into L1 and L2. So we're going to use one of them for X. So like L1 is your X variable. L2 is your Y. So I'm going to put it like this. Shoe print, height. So list or stat, edit. I need to clear what's in there because I didn't clear it from the other day. So I'm going to go up to L1 and hit clear, enter, and it clears them all out. Or you can always clear the memory. But if you go up here, hit clear, enter. Now I'm going to put them in. All right, so you should have your L1 and L2. So now we are going to find the R. One thing we have to remember is turn on stat diagnostics. Because if we just go in and go stat, calculate number 4, sorry if you can't see that. We're doing 4 for linear regression. And then it gives us X list, Y list, calculate. It's going to give us like our linear equation. The thing that we're missing that we have to remember to turn on is stat diagnostics. So go to mode and then go to stat diagnostics and turn on. So mode is up here. And stat diagnostics is almost down to the bottom. And for some reason, it's always like the reset is just off. So we have to turn it back on. So once you get that, then you can go through and do stat, calc, linear regression, calculate. And we want R. We're going to do to 3 significant digits. Did it work? Okay. All right, so let's look at where this would fall in our correlation. So it is positive. But it is not very strong, right? It would fall kind of in here. So it's just a correlation, positive correlation. Okay, so let's go to the next page. Hold on a sec. All right, so now we are going to look a little further. That's where we would stop in college algebra. So we're going to look at also some critical values because we also need to take into consideration how many samples we have. So if we look over here, we have 1, 2, 3, 4, 5 in our sample set. We only have 5. So it's a small sample. So we can take that into effect to see if this is a good correlation or not. So we are going to use a table of special values. So we are going to, whenever you have tests and stuff, I'm going to give you the tables that you need. And they might actually be on Pearson as well. I'm not sure. I'll have to check that. But if they're not, I'll give you those. So it says, for now, we're going to use a table for deciding whether there's a linear correlation. Look at the table for N number in the sample. and match with critical values. Compare the correlation coefficient against your critical values. So we have this table. So we had 5, right? So we're going to look at this one. So our critical value is 0.878. Now let's look at this chart. This is a number line so we can compare. So we have 0 in the middle, -1 to the left, +1 to the right. We're going to look at our critical value. This critical value is going to be plus and minus. Because if it's a positive, then that would mean you have a positive correlation, or you could also have a negative correlation, so that's still a correlation. So we plot those critical values on our number line. So see how they have 0.878 over here, -0.878 here. And then you look at what the R value that we got from our sample data. So anything that is between your two critical values means no correlation. So I'm going to put it right here. Between CVs means no correlation. This is where our data fell. And then if it's in the left tail, let's say it came out over here. This is your left side. No, right side, sorry. I don't know my left and right today. This is the right side. So if it's on the right side past your critical value close to 1, then that would be correlation. If it's on the other side close to -1, that would mean a negative correlation. So from our sample data that we got, it was between the critical values, meaning no correlation. So let's fill in the blanks here. The linear correlation coefficient of R equals R. This was our sample data. So this is sample data. And it was computed from the paired sample data. It's a value that lies between the critical values, R of 0.878 and -0.878. So it's between those two. So if it's between the positive and negative of a number, that includes 0. Anything that has a 0 correlation is no correlation. So this is equivalent to no correlation. So therefore, we do not have sufficient evidence to conclude that there is a linear correlation between shoe print length and height. So in algebra, we just find the R and we say correlation, no correlation. In statistics, we go further and say, do we have enough information to say there's correlation or not? So this one, we didn't have sufficient evidence. So in order to back the data, we have to have evidence, and evidence is found from your critical values. So that's how it is written up here. Correlation, if the computed linear correlation coefficient lies to the right or left or right tail region beyond the table values for the tail, conclude that there is sufficient evidence to support the claim. And then no correlation if the computed linear correlation coefficient R lies between the two critical values, conclude that there is not sufficient evidence to support the claim of a linear correlation. So this was in the left or right tail, and then the other one was between. So we're going to look at some data that's already been calculated for us. So for a data set of chest sizes, distance around the chest in inches, and weights in pounds of 4 anesthetized, is that what that says? Bears that were measured. The linear correlation coefficient is R, so that is from the sample data. Use the table below, well, above, actually, to find the critical values of R. Based on a comparison of linear correlation coefficient R and the critical values, what do you conclude about the linear correlation? So let's start filling in the blanks here. The linear correlation coefficient R equals 0.998. That's what was computed from paired sample data. We need to find our critical values and see how they compare. So we have to know how many were in the sample. 4. So look back up here. Our critical value is 0.950. So it's also plus minus. So it's both of them. So I'm going to put it here before I put where it lies. So 0.95 and negative 0.95. So I'm going to draw a little table here. A little number line. So on this number line, we need our critical values. 0.95 and negative 0.95. So anything between is going to be no correlation. Anything outside of it will be a correlation. So where does our computed R fall? So it would fall really, really close to 1. 0.998. So let's fill in the blank here. The value that lies blank the critical values. What do I put? Outside? Because it's either between or outside. Or above or below, between the critical values. Therefore, how do we fill in the blank here? Yep. We have sufficient evidence to support the claim that it's a linear correlation. So therefore, we have sufficient evidence to conclude that there's a linear correlation between chest size and weight. Okay, so that is it for chapter 2. So make sure to complete your Pearson assignments.